Okay. Hi, everyone. Welcome to the recording of lab 3B problem 4. So this lab is about proving that languages are about how to prove languages are not regular. Okay. So to prove that a language is not regular, what we do is we give an infinite Fooling set. Okay. Infinite Fooling set. So what do we mean by a Fooling set? Okay, so a Fooling set is a set of strings, such that for for any pair of strings, okay, for any pair of strings in F, so F is our Fooling set, there exists a distinguishing suffix. So let us parse this definition one by one. So let's see. The first thing is it is a set of strings. This is easy enough to understand. A Fooling set is a set of strings. And what does the set look like? It is like for any pair of strings, we have a distinguishing suffix. Okay. So the only part that is unclear over here is what do we mean by a distinguishing suffix? Okay. So what does a distinguishing suffix means? So if I give you two strings s1 and s2, okay, a distinguishing suffix s is a string s. So if s1 and s2 belong to sigma star, then s is a distinguishing suffix if s also belongs to sigma star, and s1s belongs to L and s2s does not belong to L, or S1s does not belong to L and S2s belongs to L. Okay, so why is this called a distinguishing suffix? So suppose you have this machine, okay, let's say we have a DFA over here. Okay, this starts at some start state S, and on S1 it will transition somewhere because it's a DFA. It is going to end up at this one particular state at the end of S1, right? And on S2 also it starts and it ends up at some state S2. Okay, so now because it's a finite automata, multiple strings can reach the same end state, the same final state, right? So we could potentially have S1 and S2 reaching the same state at the end of it. But if we have a distinguishing suffix for S1 and S2, that is a string S such that either this holds or this holds, then what will happen? Let's assume that this is going to hold. Okay, S1s belongs to L and S2s does not belong to L. That means if I start from this start state S, I see S1, I reach over here, okay, at this state over here, then I'm going to see S and I'm going to reach some state which has to be the except state. Okay, and when I start from S and I see S2, then I reach this particular state over here. On seeing S from this state, I will reach a state which is not an except state, right? Because S2S does not belong to it. So S1S and S2S have to reach different states at the end, okay? Because one is reaching an accept state, one is reaching a reject state. And because this S is same, and the suffix S is same, that means S1, S2 themselves have to reach at different states, okay? So we cannot reach at the same state from here, which is why it is called a distinguishing suffix, because it tells us that if two strings S1 and S2 have a distinguishing suffix, that means S1 and S2 reach two distinct states starting from the start state S. Okay, so a Fooling set is a set of multiple. So a Fooling set is many strings in it, such that for all pairs of strings Si, Sj, for all ij. Okay. Okay. Si is written this way. Okay, so for all Si, for Si comma Sj, there exists a distinguishing suffix. So Sis belongs to L and Sjs does not belong to L, or vice versa. Okay, so basically what this means is, whatever my Fooling set F is, for each pair of string, for every string in my Fooling set F, I need to have a different state where the particular string is ending. Okay, so what this further means is, if I can show one infinite Fooling set, okay, just one, if I show one infinite Fooling set for a language, that means that any DFA that I have has to have infinitely many states. Okay, has to have infinitely many states, which is of course not possible because it's a finite automata. Okay, which is why giving any one infinite Fooling set for a language proves that the language is not regular, because we prove that a DFA, a finite automata, cannot exist for it. So if you want to, so this might be an easy way to remember how to prove languages are not regular. If I give you a language L to prove that it is not regular, okay, then you give me an infinite Fooling set. It is very important that this Fooling set is infinite. Okay, and if once you give me an infinite Fooling set, I will pick any two pairs of strings and give them to you. Okay, and you give me a distinguishing suffix for them, SIS, SJS, where S is a distinguishing suffix. Okay, so try remembering this as a game. I ask you to prove that a language is not regular. You give me a Fooling set. I pick two pairs of strings and give it to you, and you give me a distinguishing suffix. Okay, so I can pick any pairs of strings. So you need to have a distinguishing suffix for all pairs of strings over here. Okay, so okay, so that's it. So I would like you think for a minute. Can a language have multiple Fooling sets? Can a language have multiple Fooling sets? Okay, so I would suggest that you pause the video over here, take 5 seconds, think, and then restart the video. And the answer is yes, a language can have multiple Fooling sets. Like just all subsets of Fooling sets will also be Fooling sets. All subsets of any Fooling set, right? Because the definition of Fooling set just says that it is a set of strings such that for any pair of strings, we have a distinguishing suffix. So this is, if it is true for a set, it is true for every subset of it. Okay, so a language can have multiple Fooling sets. So in particular, a language might be might not be regular, but you can always give a finite Fooling set for it. Okay, you can always give a finite Fooling set for not regular language also. So giving a finite Fooling, if you give me a finite Fooling set, you're not proving anything about the regularity or the irregularity of the language. Okay, non-regular language can have a finite Fooling set. A regular language can also have a finite Fooling set. So to prove that a language is regular, you have to give a finite NFA or DFA or a regular expression. To prove it is not regular, you have to give an infinite Fooling set. These are the only two ways. Giving a finite Fooling set is not going to help in proving the regularity or the irregularity of a language. So this is an important point to note. Okay, so let's move on to the question. So we want to find all strings over 0, 1, where number of zeros is exactly twice the number of ones. Okay, so let's see this. Okay, so intuitively speaking, I want to accept all strings such that number of zeros is twice the number of ones. So to solve a Fooling set problem, try to think of where it is going to fail. Okay, a finite automata will fail at points where it has infinitely many things to remember. When the number of things to remember becomes too much, a finite automata cannot handle it. Okay, by too much I mean non-constant, okay, or non-finite. So if it has to remember a variable which can take values over all possible integers, so that is not so that cannot we cannot have a finite automata for doing that. Okay, so over here I basically want to remember the total number of zeros that I have seen. Okay, so now some of you might think that you can bypass this problem by for every two zeros you will cancel out a one. Okay, and this bypasses the problem of remembering too many zeros or too many ones. But the problem with this approach is I might have a bunch of zeros at the beginning, many zeros, and then the ones start very late. Okay, so my first canceling is going to happen very late. Okay, and I have no idea how soon this is going to happen. There are just too many zeros, so this algorithm fails over there. Okay, now when you try an algorithm and it fails, that should kind of give you an intuition of how the Fooling set is going to look like. Okay, scratch that. When you try multiple algorithms and all of them fail, that should give you an idea of how a Fooling set is going to look like. So for us, it works in our first algorithm. Okay, so my issue for trying to design an automata for this is I might see too many zeros in the beginning, and I have to remember every one of these zeros. Okay, I cannot not remember how many zeros I've seen, and that is too much for my automata to handle. So my Fooling set is going to look kind of like that. So my first thought of a Fooling set is look at all string 0 star. Okay, but the thing is that number of zeros is twice the number of ones, right? So number of zeros is even, that much I know. So to make things easier, I will say let my Fooling set be all strings, all zero strings of even length. Okay, so 0 to the 2i belongs to n. Okay, so this is my candidate Fooling set. Let's see whether this serves our purpose. So I have given you a Fooling, or let's say, to keep up with our terminology, you gave me this Fooling set. So I'm going to pick any two arbitrary strings from this Fooling set. How do they look like? 2 to the I, 0 to the 2i, 0 to the 2j, I not equal to j, right? So, and now these are the strings that I have given you. Now you have to give me a distinguishing suffix s. So I would suggest you again to pause the video for 10 seconds and think of what a distinguishing suffix should be. If you can figure out the distinguishing suffix, then I think you have understood Fooling sets, or at least distinguishing suffix. But yeah, okay. So okay, so what would a distinguishing suffix for this be, right? So I want one of them to belong to L and one of them to not belong to L. So let's say I want this string to belong to the L over here. Then I can only add 1 to the I, right? Because, yeah, adding 1 to the I makes it in L, okay? And if I add 1 to the I over here, so I is not equal to J, so 2J is not equal to 2I, right? Sorry, 2J is not equal to 2I. Okay, so this implies that number of zeros is not twice the number of ones over here. Okay, so yeah, so 1 raised to I becomes a distinguishing suffix. So for any two pairs of strings in this Fooling set, we can get a distinguishing suffix. Okay, so yeah, so this is a Fooling set for the language. It is infinite because we have I and n, so it is actually an infinite Fooling set for the language, which makes the language not regular. Okay, so that's it for this question. I hope you understood the concept of Fooling sets, and I hope you understood the explanation for this problem. Thank you for listening for such a long time, and all the best. Goodbye.